Hello, I'm David Chin. This is my Physics 1 Lab 3 report. So this lab was intended to estimate the mass of a black hole using known properties of rotational and gravitational motion, and we generated models for both cases using GlowScript, and the other case was simulating the motion of a spaceship orbiting a star and a moon. The overall system is a star, planet, spaceship, and a black hole, with the addition of a moon in the last portion. So some basic equations, Newton's second law, net force is equal to the change in momentum divided by the change in time. And since the spaceship is following the properties of rotational motion, the equations for net force and perpendicular and parallel directions can be used. And we can also use the force-gravity equation because we assume that's the only other force acting on the system. And on the previous slide, the moon will have an effect on the second part, but not on the first part. And so lab overview from the previous slide, we can use these four equations as we assume that there is only a force of gravity with these objects and there are no other external forces acting on the system. And it's also important to note that the force of gravity isn't constant as the radius of the spaceship is constantly changing. And yeah, we can calculate the mass of the black hole through these net force and force of gravity equations. And so here are some initial values. We have the gravitational constant, the mass of the star, and the time steps, which is the amount of seconds in a day. We also have the mass of the star at 2 times 10 to the 30 kilograms. And so to find the net force, we use the difference in momentum across time steps using Newton's second law and equating that to the force of gravity equation to isolate big M as the small m, which is the spaceship, cancels out over time, or over both the equations. And so to estimate the mass of the black hole, like I just said, you average the mass at each time step. But this is GlowScript, so you average the mass at each time step to obtain the final result. And since the spaceship starts at the origin, and other initial conditions were described before, we can find the mass of the star using a simple rearrangement of the variables, like I said before. And my estimated mass of the black hole is 1.341 times 10 to the 44 kilograms. You can see this is the basic equation for mass of the black hole, which is just rearranging the F-net equations. So for part two, this is finding initial velocity of a spaceship so it doesn't crash. So we played around with the initial velocity a lot. We settled on 2.5 times 10 to the 4 for both the direction of the y and the x for the initial velocity of the spaceship. And you can see here that we have our initialized conditions like the mass of the planet, the mass of the moon, the mass of the ship, and we have initialized velocity here. And so, as you can see, this code has the basic parameters for the spaceship's motion, and you can see that on the left that the spaceship does not crash, and it makes a figure-8 motion around these planet and the moon. And you can see that here we have, if the spaceship crashes, we print out this line of code and we break the code, so we are notified that the spaceship crashes. And so through this area of code, we were able to find the initial velocity, so the spaceship wouldn't break circular motion and wouldn't crash into either of the planet or the moon. So for some sources of error, our main source of error was troubleshooting initial velocity and finding one that wasn't too large as the ship would break orbit, or too small as it would be not able to resist the force of gravitational pull, which means it would crash into the planet. There were also troubleshooting some of the multiple values of the black hole that were generated, but we were able to find one through averaging the all the ones generated, as we have back here. Yeah, in the average equation right here to find the most accurate mass of the black hole. And then there could also be error in a realistic system, as we assumed only force of gravity was persistent in this experiment, which would not be true in a system actually orbiting a system of, or a spaceship orbiting a system of a planet and a black hole. And so the key difference between net force and rate of change of momentum is that net force affects the rate of change of momentum as it consists of the actual physical forces acting on the object. In the parallel direction, the force net would affect the speed, and the perpendicular direction, force net would affect the direction, and rate of change of momentum is just a simple way to say how the speed of the object is changing. And for the imaginary system, we would still have the same equations, just because we would assume again that there are no external systems. And the most dominant interaction would be between whichever gravitational pull has the most mass, as that would increase the magnitude of the gravitational pull to be greater than anything else. Thank you.